So there were two pending issues from last class. One is this formula where there is extra p that was missing, right. So yeah, we need an extra p, that's all. So it is total of n trials, out of which so n trials, out of which r are successes and n minus r are failures. So that missing p is back. Okay, so it should be p to the power r. This is basically p power r. Okay. So if you want to rewrite this, it is that's what it turns to. Right. So that way we have r minus 1 failures, sorry, r minus 1 successes in the previous n minus 1 failures. Okay. So this was one clarification. Then the other clarification was to why do we need this d plus n minus 1 business, right. So we have min of dn, that makes sense, right, because you cannot have the maximum number of defective samples or whatever it is that you are trying to select from that box is bounded by d, right, or if it's you are taking d is less than n, then it's got to be n itself, right. If you only take 3 samples, there are 20 defective items, then you will have at most 3 defective items, which is what k is representing. On the other side we have k is something max 0 d plus n minus 1. So did I tried to explain it, but you are all busy with your tutorial that people didn't pay attention or didn't care about it at that point in time, right. Okay, so what is the explanation for this?
Non-defective items cannot be negative.
Yeah, so the number of non-defective items cannot negative. Okay, let us fix that. So let's go back and explain that, right. So if I have a system where I have total of n items, right, and I have a total of d defective items, right. So there are n minus d non-defective items, right. And if let's see my condition here, yeah. So this the condition that we want is, okay, so I am picking n samples, right. So k is the number of defective items, right. And the lowest possible value for k would be if, okay, let's see, so if f n is less than, okay, I will do an example, I will get this right. So what is my example here, yeah, so n equals 20, d equals 16, right. So if I have 16 defective items in a total set of 20, right, so the non-defective items is 4, right. And if I let us say choose, okay, if something go back there, right. So if n is less than or equal to 4, right, what will be the minimum or least value of k? If I pick only 4 items, right, then what can happen? What will be the least number of defective items? It will be 0, right. Worst case I could get no defective item at all, but if n equals 5, then I have to pick all, right. I will have at least one defective item that I will end up choosing, because there are only 4 non-defective items. Therefore I will in the 5 experiments I could have picked the first 4 times I could have picked the non-defective one, the last time I have to go and pick the defective one. Therefore min value of k is, so the minimum value of k is 1, right. Okay, right. So therefore let us go to the next page. So if n is greater than n minus t is where you will have that condition, so then your k will be so your k has to be greater than or equal to n plus d minus n, right, make sense. So that is where that so that is why k has to be either 0 or something else, right, max of this and that. So if you are still not convinced, you can go back and work it out, right, that is okay. So that is where we stopped off last time with all those different variables. Okay, any questions on the discrete types? I know initially it looks like a lot of sort of math up in the sky, but just to get you back thinking about some of this, we will have to go through some definitions. In the past I have simply gone straight into Markov chains without giving much of the background, but this time I thought I would give you a little bit of rigor. So a lot of this stuff is there in our Rod Jain's book too, all these variables are there in the chapter that I mentioned. One of the things is not much explanation, simply a list of variables, but I thought some more explanations is needed. Okay, so that about finishes all the discrete random variables that we have covered so far. So any questions on this? And most of these we encounter, right, on day-to-day basis. So depending on what we use, later on we will choose one or more of these type of variables, right. Questions? Okay, so now let us look at this one property called the memoryless property. Memoryless property where we look at both discrete variables as well as continuous variables or random variables. Okay. So which variable or random variable in the discrete set has the memoryless property? Geometric, right? People agreed, or is it the first time you are hearing that? How many of you are hearing it for the first time that the geometric is memoryless? Okay. Geometric is memoryless. Okay, so you have not heard it before. Only those who did the math course. You did this in which course? Your probability course in math. Okay. So you are waiting for the to get rid of probability. Have you done Markov process then? Not. Okay. So when we get to Markov, then you will see something new. Right? Until then, just bear with us. Okay. So let us look at this geometric, right, variable and why that has this memoryless property. Okay. So the idea of geometric is keep tossing until you find the first success, right. So the probability of the number of trials needed is what is described by this geometric distribution given your parameter p, that is a single parameter. Okay. So now let us say that right, we will use some variable z, right, is the number of trials till the first success. This is z, okay, and so if you are trying to transmit a packet, right, so this is the number of trials till the first success. Let us say you already tried transmitting this packet some okay, n number of times, right. So you have tried n times, and I have to do a lot of editing in the audio. So n times you try, and then it has been failures. So the first 10 attempts are failures. Okay. So z is the total number of trials, and n is the first n attempts which have all ended up being failures. So I use this variable y, right, this is the exact definition, number of additional trials needed. So the random variable y is the number of additional trials that I have to do before I encounter the first success. Now I want to see what the distribution of this y is. Given the fact that already the first 10 times have been failures, will that make a difference to my probability, right? Till the first success. So this is Z is the total number of trials. I have done Y and I am looking for, I have done N, which is failure. So Y is the representation for. So after conducting N experiments, I am looking at the distribution for Y and see whether it has the same distribution as I started with initially, right.
So after N plus Y, I will get the
First success, yeah. So I am trying to find out whether the distribution for this variable Y, right, what is the distribution for that, right. Given that we know that first N is failure.
We are trying to get that is Y is independent of N.
Yeah, the distribution for Y is the same as when you started at the initial distribution, right. The initial distribution for Z we know, that is P into Q times I minus 1, right, or whatever the variable that we are using, right. So if it is P into Q, Z minus 1, that is it. Okay, so that we will do as a conditional probability, right. So so I want to find out what is the distribution for Y equals I, given that Z is right. So what is the distribution for Y, given that Z is greater than N, which we will just spend a little bit time deriving, because everything that we use later on depends upon this business of memoryless, right. So when you go to Markov chains, whether discrete or continuous, we end up having this memoryless property. So that is why we are trying to derive this. I given that okay. So how do you proceed now? Let us recollect your probability skills. So how do I, what is the probability distribution here? What is the probability distribution of A given B, or conditional on B? Of A and B divided by probability of B, right. This goes back to our probability days. So if you do not remember that, suddenly this is coming in new, then you should go back and look at that first definition, okay. So this is basically what is the probability that Z equals Ni and Z is greater than N divided by Z. Z is looking like 2, just ignore that. Okay, I will do this dash. So Z equals for any value of I greater than 1, right, the second part of the condition is redundant, right. So this second part I can simply ignore and just say what is the probability that Z equals N plus. See, if I equals 1, right, so if Z equals N plus 1, it is naturally greater than N, right. So therefore the second part of the conditions is subsumed by the first part of the for all values of I greater than 1 or greater than equal to 1. So what is the probability that P equal Z equals N plus I in our whole node, that is P, we use Q to denote 1 minus P, right. So this is simply Q N plus I minus 1 divided by so this is the probability that minus 6, right. So this becomes Q. So Pz greater than 1 simply means that all the N trials were failures, right. So what is the probability of all the N trials being failures? Q to the N, right. So we will simply put that as Q to the N. So if you remember a definition, what is the probability that y equals I given that z is greater than n is simply that. So you can see that there is no dependence on n at all, right. This is the original distribution we started with. If I had simply said what is the probability of taking 4 trials, it is simply p into q3, and even after 10 trials, 100 trials, it does not matter, the probability does not change. This is what is called as a memoryless property of the geometric variable, right. So this is the same as the questions. Okay. Okay. So then we have done with the discrete random variables so far. No questions? So we will go to the exponential now. So the same property in the case of continuous random variable is shown up, shows up in the exponential random variable, right. So how do you go about proving this? Now that I have proved this already, the other one, right. Let us formalize it.
Probability of s x greater than s. Sorry, given probability of x greater than s plus t given x greater than s.
Okay, let us try that. Okay. So here what we are having is, see, there is something, right, happening in the time axis. Usually we look at it as time, right, inter-arrival time or something like that. So this is, let us say you are just waiting for the bus to arrive, right. So you have started at time t equals 0, right. And you have waited for some time, okay, we will call this uppercase T, right. So you have waited for such a long time for the bus, and then you want to know how much longer will I have to wait, right. What is the distribution for the remaining waiting time? Normally what do you expect? If you know the bus is coming every half an hour, if you waited for 20 minutes, you know that the probability of the bus coming next 10 minutes is fairly high, right. So but here we will try to look at, so given that, right, so x is my random variable and I use this little x, right. She used s and t, let us try with x and t, right. So what is the probability that the arrival will be before this time x, okay. So we said what is the probability that x is greater than x plus t given that x is greater than t, right. That is the probability we want to prove. And so this probability x greater than will also give me the distribution, right. So if I solve it and I know that it is a known distribution, then I will end up with that. Okay. So how do we go about this? So we do like before, what is the probability that x is greater than x plus t and x is greater than t divided by the probability that x is greater than t.
So our random variable x is that the event is the non-arrival of bus.
The arrival of the bus.
Then you have taken x is greater than t.
Okay.
Okay, means
So which means that so what is the say to get the distribution for this I can get the we can also derive it the other way if you want. Okay. So let's
it should be non-arrival of bus.
okay. We'll look at arrival of bus then, right? So what's the probability that the bus will come before t plus x, given that I have waited already for t units. I am just redefining this original thing, right? So this makes sense, right? So this I can write as x is right. So I remember that again conditional. So this one to be to x2 should be greater than t and x should be less than x plus t. So therefore this is my condition.
We have written small t.
Capital
Mix up this and that. See, I'm trying. Yeah.
In the timing diagram view on the other page,
Mm-hmm.
that small x is the duration between the capital T and that time bit.
No, x is yeah correct. Yeah correct.
The duration.
Yeah duration. Yeah. And this is t. We used a, right? So we are looking at the total, the distribution of this variable x, right? So this is the same as the CDF that we started with, right? 1 minus e power minus ax or lambda x. That is CDF of x before we started, and the CDF of x even after time t units, right? So that's why, therefore, the fact that you waited for this much time does not make a difference to the probability as such. So if you want to look at this pictorially, right, this is your time axis, right. So the distribution was something like this, right. When I started, this is a distribution for the waiting time for the bus. Now I waited for t time units. So let us say I have shifted my axis, right, and it's still going to be the same. So it's simply time shifted by t. You can write this mathematically also, right, but anyway, that I leave to you. That whatever probability x of x minus t is the same as x. So this is again, these are the two sort of classic memoryless properties, right. And this is only applicable for these two distributions. So in general, if you find a random variable that you are studying and measuring, right, continuous random variable that has this memoryless property, then you can state that it is exponential because the only one that has a property. Okay, so that is we touched upon exponential, the memoryless property. Now we look at 2-3 sort of derivatives of this exponential, and then that point will stop with all our random variables business. Okay. Okay. So next look at hypo exponential, because it comes often when I deal with the networks of queues, chain of queues. Right. So yes, for the rest of this I am going to use lambda 1, lambda 2 and so on, because that is what is there in this Trivedi's book. So just for whatever A I call before I am going to call lambda now, so do not get confused, right. So what you have is you have a process, right. So you have your going through, right, your entire system is going through several phases. Let us say this is a pipeline, right, and you are going through these phases, and each phase you spend a certain amount of time, right, and the time that you spend is okay, that is simply not working out. So this is phase 1, phase 2 and so on, a total of r phases, okay, and the time that you spend in each phase is lambda 1, lambda 2 and so on. So this is exponential at each of these cases, right. So before I give the general, so if I have only 2 phases, right, so what is the distribution for f of t? So for lambda 1 not equal to lambda So whenever you have a concatenation of phases with each of them, you know that there is a particular this exponential distribution, you know the parameter, then you know the distribution of the entire parameter of the entire combined process. Okay, so this is your f of t, and just write down ft for the sake of completeness. We may not use each of these formulas in future, but just for completeness sake, and because also these notes when they go on the web or on YouTube they will have this. So this is for a 2 stage process, right. Many times you have 2 stage process. If I want a generalized n stage process, then it is can you define that?
What does the random variable capture here?
So this is what it is capturing is, so if I have like an assembly, right. So let us say you are spending time in 2 queues, and the service time in each queue is exponential, right. So you are spending time, let us say you have you are going to a bank, right, and you are first have to stand in teller 1 where you have to wait for the service, right. You just go to the teller 1, this is not, let's not look at waiting, simply service time at the first teller for whatever process you are doing is exponential with this parameter lambda 1. then you get shunted to another person who will again make you, right, he has to service you, and that is also exponential time with service lambda 2. So then you have two separate processes but one follows the other, then you have this hypo exponential. So the overall waiting time, yeah, so T is your total waiting time in the system, yeah, correct. Yeah. Okay. So that is one variant of exponential. Okay. Then another variant, so we have done series, what could it be the other thing? Parallel, right? So I have a process that can take one of say R phases, and but each of only one of those R phases, it's in parallel, right? So you go to the bank, either you go to the DD counter or you go to the cash withdrawal counter or you go to some passbook update counter, you only do one of these three things, and each of those you have a known distribution that is exponential with the parameter lambda 1, lambda 2 and so on. So in that case, what is the average waiting time? So this appears not just in the bank but also even when we look at CPU processes, right? The process comes in and sometimes it goes to IO, sometimes it goes for computation, sometimes it goes to I don't know whatever, say just writes data to files and so on. So each of those will take different times, but you want to look at the overall distribution for the process in general, because maybe you can try to prove some properties, right, if you know the overall distribution. So that's why this is useful, right? So that's your hyper exponential. So the right, so there is the process, or that your here process is not our stochastic process, simply that this is a random variable, you are going through some system, right, I would say system has say R, right, alternate phases, and each time you are tossing this coin or whatever it is, you are going to go through only one of those through phases, right. So what is the overall distribution, and you know that each of these distributions is exponential, right. So that's where your f of t is now. So this is again simple, so there is lambda I e power minus lambda I t, there is simply another, so you know the probability of going to each one of those phases, which is alpha I, right. So with probability 0.3 you go to one phase, 0.4 you go to the summer phase and so on, and therefore this is simply the summation of all those, where your alpha I sums up to 1. So that is why I wanted to get that MATLAB, so we can plot some of these things and see what, because sometimes you find that certain distributions fit hyper better or hypo better or hyper better than simply purely exponential, right, and the exponential is still the easiest for getting closed form, but for more complicated systems you may find that hyper better fits, because you can actually describe the system that particular way, right. And so as such it's similar to what we had, except this alpha I parameter, right, that's all. And if we are looking at so what is the expected value, alpha parameter is the probability of going to one of those three phases. So a customer entering will go through one of those three tellers or counters with some probability alpha, that is predetermined. So that is part of your input. Input tells you what is alpha and what is lambda I, right. So what would be the expected value for this? What is the expected value for a exponential variable, 1 over lambda, right. So you can just guess what this can be, simply alpha by, we can prove this with taking a whole class, but So that is the expected value, and again if you look at the E of x squared, that is also similar, right. Because in the case of exponential, what is the E of x squared? 2 by lambda squared, right. So this is again 2 alpha I by lambda I squared, that I will leave, right. Okay. So that is the hyper exponential, right. Just 2-3 more and then we are done with these variables. Okay. So then and then we have this what is called as Weibull distribution. I do not know what I did there, but I did something which is not intended. Oh, okay. So when people were one of the things from our performance side of networks and so on, we normally look at exponential and many other things for the service time, right, the time spent in service, or even if it is a CPU system, you look at different processes and look at the time taken by each process, right, how long does a IO bound process take and how long does a CPU bound process take, then you can you try to sort of characterize them as exponential and so on. So there is another field which uses this extensively, these variables, is reliability theory, right, where you want to look at the probable or reliability of how long will this particular lifetime of a product, right. So you want to characterize the lifetime of a product, and you start off by saying that the lifetime is exponential, right. So if you are buying a cell phone today, right, how would you characterize the lifetime of that? If you were to say plot the lifetime of this, right, or the probability of failure of this component, then what will it look like? So at every instant, right, plot the failure rate or the likelihood that this item will fail.
We will observe it for some n number of days. We will see how many times it has failed. We can just number of times it has failed divided by n, if n is 6 months or so. We can just calculate.
So if you had to say characterize this as a distribution, right, you have looked at several devices for a long time. If you buy most of the electronics items, right, if you look at it, this is a guess, right, that very likely it will fail in the first few days or so, right. That means somewhere in the quality testing something went wrong, right. So the probability of failure, if I am plotting, it will be little bit high, right, initially, and then it will drop down to 0 for a long time, right, and then once it gets to 3 years, 4 years, then the probability of failure starts creeping up and you end up with something like that, right. That's your, and this is your lifetime, this is your, right. So if you are able to go past, if you survive, right, if your particular product survives for the first 2-3 months without any failures, then it will simply survive for a very long time, but if something goes wrong, and that is again a generalization, right. So we try to, so therefore there is this group that tries to look at the lifetime of product, reliability also, right. What is the reliability? So reliability is tied to the lifetime. At every instant of time, will this product fail or not? And it is useful in machinery, and we look at aircraft also, right. An aircraft has millions of components, and each component has a failure probability. So you want to compute the overall probability of, right. So when Boeing designs its planes, it has to make sure that at least theoretically they can give you some reliability information that this entire aircraft will function, right, without failures for this extended periods of time. So this Weibull distribution comes from that side of theory where people are looking at the lifetime of a particular product, and I find that exponential is not really capturing the lifetime, because exponential simply goes down, right, very sharply. So this, you add one more parameter, so called shape parameter, that will help you, right, define. So again, how do you determine the shape parameter? That comes from observation of the product over years, right. So you build a product, you keep on measuring its lifetime over years, and then you see what happens, right. So now yeah, how do we do this? So I have, so where I had lambda, I am scaling that by lambda alpha, and then I have my e power, instead of lambda t which I had before, I am raising that to another power alpha. Alpha is a shape parameter, yeah. So alpha is something that you will have to figure out. So your system is specified by 2 parameters, one is lambda and one is alpha. So if you are going to say this product follows this Weibull distribution, you will say alpha equals 2 or alpha equals 3 or something like that, and there is one more term, we will add that t.
Alpha is the input, sir.
Alpha is input, yeah. So the parameters for this are lambda and alpha. And this is again generalization of your exponential, right. If alpha equals 1, this becomes your regular exponential. Only for alpha greater than 1 is it's right, it's describing something else, right. So that when we get that system, then I will try to plot for alpha equals 1, 2 and so on to show, right, how the life cycle, how to describe the life cycle of a particular process. So this is again just something, right. So this is used to describe fatigue. If you look at a PC too, PC has so many things, right, your memory, CPU and so on, then very often the first thing to go is your hard drive, and you simply have to replace that, which is okay on a desktop system, but in the middle of your flight your hard drive goes off, you can hunt for hard drive and replace that, right. So based on this distribution they will plan the redundancy in the system, right, how to increase reliability and so on. Yeah.
So what are the possible values for alpha in this case?
It will be greater than 1, but to figure out a value for 1, that is usually something that you will have to either estimate over time, right.
Greater than 1.
Okay, yeah, what if alpha is less than 1? Alpha is less than 1, then my t alpha minus 1 is there. Okay, let me check upon that, right, to see if I mean theoretically yes, you would get some number, but whether products are there with that particular alpha or not is the question. Okay, so then we have covered those 3 variants, right. So any other variants of anything else tied to exponential? Something called the Erlang distribution. Erlang appears in various, or the name Erlang appears, right, yeah, the Erlang's formula and so on. So but this is the Erlang distribution. So this Erlang distribution is a specialization of your hypoexponential. In hypoexponential you have R sequential phases, each of them having different lambda i's. If what do they have are identical and IID, independent and identical distributed, right. So when R sequential phases so we go back to the exponential, right, that is the definition, that is where the sequential phases is coming in. Distribution, this is your so called IID. So the time spent in each of those phases is independent of the other phases, right, it does not depend. If it dependent, then this is a different issue. If they are independent, then and identical, right. So with the same parameter lambda, then the total time spent in the system has distribution as follows, right. So this is a hyper is alternate, this is sequential.
this is the same that when we did last year, arrival processes in queuing theory.
Yes.
They were also identical and independent.
Yeah, yeah. When you're looking at arrival processes to each of the links, then you assume that it's IID. Yeah. So in this case, the time spent in each of the phases is considered to be IID with this rate parameter lambda. Okay. And so this R, if it is an integer, it is this Erlang. In some cases, I don't know, we'll have to look at some better examples for that we can relate to. I haven't yet done that search. Is if you have non-integral number of phases, right? If you have this R is not an integer, it could be any real fractional value or real value, then you get the gamma distribution, which is a little bit difficult to grasp because why would I have some 1.2 phases, right? I will have 1 phase, 2 phases and so on, but what if my number of sequential phases is 1.2? Okay, I have to find an example for that, but for now we will just I will let you take a look at the book. You have written too many formulas today. Okay. And then one more, or normal distribution, which is also I am going to let you look at the book. So normal or Gaussian is the one that we all know, right? The one that we hope that every time I do my grading, we have this perfect bell curve for doing the grading. This is also I will ask you to look at the book. So what are the parameters for the normal? Mu and sigma, right? The mean and the standard deviation. Based on that, we can try this, and then that is useful in several different ways, right? Many times we assume that things are normal, follow the normal distribution, and based on that we do a lot of our computations. Okay, all right. That's the roundup of some of the random variables. So what we will do is, since some of these variables we do not encounter in all the kind of performance evaluations, I think I will have an assignment later on where you will find some research article that uses at least one of these things, and then you will go and look for how these are used. Otherwise right now it is just a bunch of distributions that were written on the board and you never end up seeing them again. But you see them in real life examples, how people have used these to model, right? You normally start to model with some simpler distribution and you find that your performance results are not actually matching, right? So here is one sort of classic example. Okay, so you have so usually it is the reverse that we try to do. What we have is we can measure certain things like lifetime of a product, or look at the cumulative distribution, right, for something, and then you try to fit it back to one of these known distributions, because then you want to use the distributions to do your mathematical modeling and so on, to plan for future events, right? So let us say that you have some data that looks like this for something that you have measured. You are measuring f, the cumulative, your CDF is what you are measuring. Okay, these are the measured values, and then you summarized or surmised that this would be some exponential with some lambda, whatever, 1.5. You think 1.5 is the correct parameter for your, and then you end up drawing a curve like that, looks like this, right? So this is your best fit thinking it is exponential, right. So this is for some input parameter, let us say this is the time that each process runs or each packet takes in the system and so on. So you have the measured value and you have this predicted value, then you run your theoretical analysis on using this as your input parameter, saying that my input is now exponential with this, then you compute delay, throughput, whatever it is, and you find that there is this big gap between what you think is computed as a delay and what actually is reported by the simulation. So then you know that your exponential was a oversimplification. Then you look at, okay, maybe I should try to do this Weibull or maybe some hypo exponential, maybe there are actually two separate processes that is going on, right. So in your even your single mobile phone also there are two phases, one is a normal phase and one is when the wear and tear starts showing up. So even your machinery will have the same thing, right. Normally everything is working good, once the wear and tear starts showing up, then you go into the second part of the system, which will be another where the lifetime will be totally different, your parameter for that will be different from the first part of it. So then you find some other hypo or hyper or whatever it is, right, and then you find that maybe I can use color here, no, okay, this is highlighter, okay, then you find something else, right, that is better in terms of the distribution itself. Your parameter estimation is okay, but you just need a different distribution, right, you had to change your alpha value. So that is where some of this these other distributions come in handy when you are able to better predict if you try to think it as something less simplified than what you book as started with.
Now we are assuming that it is an exponential curve. It means there is some suppose it's an algebraic equation.
Yeah, so that is also, it could be something that does not fit anything at all. So we just use this as a convenience for some analytical purposes.
High degree polynomial will also look something like this.
Yes, you could try to fit it with that, but the thing is with that assumption, can you, let us say you are trying to assume that you are doing some queuing analysis, right. So you know there are results for MG1 and you are trying to say that okay I can but for if it is something does not even fit, you are assuming that the arrival process is Poisson, right, and if it is not Poisson, then if you want to get some additional information, right, so then you might say okay I have to use something besides Poisson as the arrival process. Right. Whereas if you can fit it, but this is not just curve fitting alone, right, you are trying to find out, you are trying to describe the distribution for the process and based on that you want to do some analysis, right. For example, you want to predict variance, then you know the variance for this is going to be different from the variance that you observe, right, and based on variance you are going to do some measurement in terms that you are doing some say resource allocation, you want to allocate buffers based on the variance in these times, then you find that your original variance calculation is not adequate because you are finding that you allocated certain number of buffers and then the buffers keep overflowing because your assumption was incorrect. So you want to look at a more stronger assumption. You will not get the perfect answer because sometimes there is possible that it really does not fit any distribution at all, but you want to do the best guess for planning purposes, for performance purposes and so on. So the standard assumption that was used, right, even now in industry is that how long does the average cell phone call take, right. In those days they measured, they finally said okay this is exponential with period with average of 5 minutes, that is this was what 70s and 80s when phone calls were very expensive. So that is the normal you will still see, right, exponential call with 5 seconds 5 minutes of holding time. Today it is not that case at all. So you will find that call time maybe it is not exponential, it may be something else, and that 5 minutes is also right, there are multiple values for that. Business users would have less time, whereas general chatters would have more time and so on. In that case the way you provision the system, the number of channels you allocate to a system will depend upon that, right. So that is where these things will be useful for predicting what resources to allocate, that is another side of the picture, right, not just performance alone. And also if you are going to be setting performance goals, then again you would have some understanding of what this is, right. So if you want to set the delay to some 300 milliseconds and so on, you should know that it is a feasible delay that the system can actually deliver. For that you need a proper characterization of your traffic, right. So in the networking field at least we have few models, we have the old Poisson model and exponentially varying packet lengths, we did that when we did MM1, right, but who said packets are exponentially length distributed, it is not, it is bimodal, right, many times it is bimodal. So what do you do, then you will have to somehow fit a bimodal into this, right, and then use that to get your better understanding of the results. And then they said this is self similar, it is not Poisson is memoryless, no it is not memoryless, the distribution is self similar, which means it depends upon the previous distributions also, the previous packet lengths too. And then they also looked at for video, for example, they said this is more of a Markov MMPP or Markov modulated Poisson process, not a simple straight Poisson process. So all these things people propose, they validate, and then they, but ultimately you never really know how the data files are going to be, right. What is the typical distribution for the number of packets in a particular video frame, that is still kind of unknown. So you end up with traces, so you try to do a combination of all this. So that is our end of random variables.